Welcome to CSAI Think Tinker Learn. Today, we are rebuilding the engine as we explore the new SQL Blueprint. This is part of our System Design Essentials series, where we provide a high-level mental model of the industry's most complex architectures. For full article and visual guides, visit our companion site. The link is in the description. We are keeping these videos short and conceptual to give you the big picture quickly. If you want any deep dives on any specific consensus algorithm or timestamp math or any other topic that you deem will be helpful for the general audience, let us know in the comments and we'll make sure that we will bring out that article or that topic for you. Before we start, please hit that like button, share this video, and subscribe to help us grow. Let's look at how we scale distributed transaction without losing asset guarantees. In the early 2000s, internet scale traffic hit the traditional SQL ceiling. Research from MIT and CME revealed a broken state. In a classic database, only 12% of the CPU is doing actual data work. The other 88% is wasted on administrative overhead, locking, latching, and buffer management. Old SQL was designed for a single server world. When we tried to scale it, the gear didn't just grind, they melted. The industry first kept the ceiling via NoSQL, but it fell into the cap trap. To survive, NoSQL chose availability and partition tolerance over strict consistency. This created a fraud gap, scenarios where a user could withdraw money from two different branches before the ledger could sync. Pushing consistency violation to the application layer is a nightmare for financial system. We needed a third way. The new SQL promise is a redesign the engine from scratch. As you see in our evolution metrics, traditional SQL provides ACID but no scale. NoSQL provides scale but breaks ACID. NewSQL provides both. It gives you SQL expressiveness, strict ACID guarantees, and horizontal scale, though it comes at the cost of high architectural complexity. Systems like Google Spanner and CockroachDB represent this new breed of new architecture. The foundation of NewSQL is shared nothing architecture. In the old world, multiple servers fought over shared disk, creating a massive I/O bottleneck. In NewSQL Mesh, every node owns its own CPU, memory, and disk. Adding capacity is as simple as plugging in a new machine. There is no central point of contention. The data is distributed across the entire fleet. To make this work, we have to shatter the relational grid. SQL parsing is decoupled from storage. The abstract SQL table is shattered into contiguous physical key value ranges. For example, users A through F live in node 1, while G through M live on node 2. The application still sees a table, but storage engine sees a distributed key value map. This is how we achieve horizontal scale without losing the relational model. Each node runs a sophisticated 5-layer stack inspired by OS design. The SQL layer translates queries into operations. The distributed layer routes them. The logical layer manages range boundaries. The MVCC layer handles timestamps. And the storage layer writes to the bare metal. By isolating these responsibilities, NewSQL system can iterate and scale individual components without breaking the whole engine. The greatest danger in distributed design is split brain. If a network partition isolates a cluster, independent replicas might accept conflicting rights. Without a way to reach agreement, the ledger fractures and ACID is violated. If node A thinks the balance is $50 and node B thinks it is $0, you no longer have a reliable database, you have a disaster. NewSQL fixes this using the Raft consensus protocol and quorum commits. A write is never committed just because one node received it. It requires a majority of the Raft group, usually 3 out of 5 nodes, to acknowledge the write. This formula provides a mathematical guarantee against split brain. Even if an entire data center fails, the remaining nodes maintain the single version of the truth. To keep performance high, we use MVCC, multi-version concurrency control. This allows us to read without blocking. Instead of a writer locking a row and making everyone wait, readers look at the consistent historical snapshot at a specific timestamp. Readers never block writers, and writers never block readers. It is a pure architectural elegance that creates a little storage page for massive concurrency. But here is the dilemma. How do you synchronize time across the globe? Silent clock drift can reverse the order of transaction. Google Spanner uses true time, relying on atomic clocks and GPS to bound uncertainty. Others use hybrid logical clocks, which combine physical time with a logical counter. These ensures that timestamps always move forward, even if a physical server's gear slips. Time is the hardest problem in distributed systems. NewSQL is also ending the era of ETL. Traditionally, you had one DB for transactions, which was OLTP, another for analytics, OLAP. TiDB collapses this boundary with the HTAP convergence. It uses the wrapped log to write to both transaction rows and analytical columns in real time. You can run complex fraud detection on live data without waiting for a nightly batch job. For those who need extreme speed, there is the in-memory radical like VoltDB. By dropping the disk buffer pool and executing one thread per partition serially, it eliminates locks and contention entirely. It can achieve roughly 45 times the throughput of a traditional RDBMS for pure in-memory workloads. It's the Formula One car of the database world. Which engine fits your lineage? Google Spanner is the proprietary king of external consistency. CockroachDB is the open cloud specialist for self-healing. TiDB is the HTAP workhorse for real-time analytics. VoltDB is a sub-millisecond throughput. Choosing the right NewSQL engine means mapping your specific workload constraints to these fundamental architectural trade-offs. We have built the global architecture, a million transactions per second with zero consistency bugs. Now here is my question for you. In a global system, would you prefer the hardware-heavy, true-time approach of Google or the software-based, hybrid logical clocks used by CockroachDB? Let us know your thoughts in the comments. If this helped you, please like, share, and subscribe to CSAI Think Tinker Learn. Visit the site for more essentials, and I'll see you in the next one.